Good morning, students. In the last class, we saw about the vibration of monoatomic and the vibrations of diatomic in a one-dimensional lattice. Now we will see separately what are the modes of vibration in one-dimensional mode and what are the modes of vibration in the three-dimensional mode. First we will see modes of vibration in one-dimensional mode. Now let us consider the vibration of modes of one-dimensional continuous string of length L. Consider a string with length L and it should be vibrated in a one-dimensional lattice. If U of xt denotes the deflection of the string at the point x at the instant t. If U of xt denotes the deflection of the string at the point x at the instant t, then the waves can be described by one-dimensional wave equation. Understand? There is a string with a length capital L. When it vibrates, the deflection of the string at the point x at the instant time t will give the one-dimensional wave equation. That is dou square u by dou t square, that is equal to 1 by cs square into dou square u by dou t square, where this cs is called the velocity of propagation of the wave. Cs is the velocity of propagation of the waves. When these strings are vibrating, if one end of the vibration string are assumed to be fixed, then the solution of equation 1 will correspond to the standing waves u of xt, that is equal to a sin n pi x by L cos 2 pi nu n t. That is, when a wave vibrates or when a string vibrates, one end of the string is fixed, then it corresponds to the standing wave equation u of xt, that is equal to a sin n pi x by L cos 2 pi nu n t. Now you see this diagram. If it vibrates like this, then there will be discrete lines will be created. That frequency here, nu is the frequency, z of nu is the function. Then when we draw a graph or when we draw a diagram, then it will be a discrete waves. There will be a discrete continuous waves will be arised when you are solving this equation. So when that wave vibrates, what will be the wavelength associated with the vibration? Lambda n, that is equal to 2L by n. The corresponding frequency will be nu n is equal to Cs by lambda n. We know nu is equal to C by lambda. That is the formula here. Nu n is equal to Cs divided by lambda n, where Cs is the propagation velocity, lambda n is the wavelength associated with that velocity. As n is an integer, what will be that n? Each value of n would correspond to a particular frequency. So when it vibrates, each string will vibrate with separate frequency or with a particular frequency denoted by the letter n. Thus, the frequency reveals the discrete nature. I already told you it will show the straight line graph. That straight line images will arise as shown in the figure 1 with equidistant lines. Equidistant lines as shown in the figure. Are you understand? So when a string vibrates with length L, then there will be the lambda associated with 2L by n. The corresponding frequency for that is nu n is equal to Cs by lambda n, where n is the corresponding particular frequency. When you draw a diagram. That frequency reveals the discrete nature, a straight line graph, straight lines with equidistance. From this equation 3 and 4, we will find out the value of n. N is equal to 2LVN divided by CS. When you are differentiating this equation, then you will get dn is equal to 2L by CS. It is a constant, then it is a dVn. So this is the number of possible modes of vibration in the frequency interval d nu when the wave vibrates in a one-dimensional mode. Okay, when it vibrates in a one-dimensional mode, what will be the number of possible modes of vibration? dn is equal to 2L divided by CS d into Vn. So this is the mode of vibration in the one-dimensional mode. If it is a three-dimensional mode, instead of in one-dimensional mode, you saw only dou square u by dou x square. That is equal to 1 by cs square dou square u by dou t square. But in the case of three-dimensional mode, it will be vibrating along the x direction, y direction and z direction. Therefore, dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square, that is equal to 1 by cs square dou square u by dou t square. Okay. Are you understand? So then the equation will become, there it is u of x y, here I missed z also, here x y z. In the one dimensional, what we see? Only u of x comma t only. So a sin and n pi x by l cos 2 pi nu t. This only happens in a one-dimensional mode. When it is in the three-dimensional mode, you see the equation difference, u of x, y, and here there is an z term also, x, y, z and t. Okay, here I missed this z. So what will be the formula? A sin nx pi x by l plus sin ny pi y by l sin nz pi z by l cos 2 pi nu t, where nx, ny, nz are the possible integers above 0. Now, using this equation 8, in equation 7, it will become a second order differential equation, and when you solve this equation, you will get pi by l square nx square plus ny square plus nz square, that is equal to 4 pi square nu square divided by cs square. Here when you solve these things, you will get 4 pi square by lambda square. This equation 9 gives the possible modes of vibration in a t-dimensional mode. The frequency and wavelength now depends upon the value of nx, value of ny and value of nz. So this equation 9, from this equation 9 you cross multiply nu square here and you cross multiply all the things, you will get cs square divided by 4l square nx square plus ny square plus nz square. But we know that k is the wave propagation wave vector and its value should be 2 pi by nu by lambda, 2 pi by lambda, or 2 pi lambda is nothing but nu by cs. We know this formula. So what will be the components along x direction? Kx is equal to pi nx by l, ky is equal to pi ny by l, kz equal to pi nz by l. Okay, so the components of the wave vector are, because we already know it is a three-dimensional mode, therefore in three direction there will be the motion takes place or the vibration takes place. So each vibration there will be one wave vector. So for along x direction one wave vector, y direction one wave vector and z direction one wave vector. Therefore kx is equal to, the above equation can be changed as kx is equal to pi nx by l, ky is equal to pi ny by l, kz is equal to pi nz by l. Okay, right. Now We will see this later. Here you see now nu square is equal to 4s square by 4l square into cs square divided by 4l square into, this is equation 10. You see the equation 10, then you will understand. L by pi the whole square, kx square plus ky square plus kz square. Where from that equation 12, when you cross multiply it, kx is equal to nx pi by l. So from that you will find out, from the equation 12 you will find out nx square plus ny square plus nz square, that is equal to l by pi square kx square plus ky square plus kz square. But we know that, now you come this, but we know that kx square plus ky square plus kz square is nothing but the combination of a wave vector k square. Therefore, instead of this you substitute. So, nu square, that is equal to cs square by 4 pi square into k square, or nu is equal to csk by 2 pi. Nu is equal to csk by 2 pi. So, this is the frequency when the modes in a three-dimensional space. In a three-dimensional space, the frequency will be csk divided by 2 pi. Now, how the frequency should be distributed in 3D? If k is the wave vector, kx, ky, kz and r is the position vectors. Kx along the x direction, ky along the y direction, kz along the z direction and r is the radius of the vector. Then from the equation 12, reciprocal space, it represents the reciprocal space or momentum space. From the equation 12, it represents the reciprocal space or momentum space. Here you see this is the diagram. K, this is along the kx direction, this is ky direction and kz. In some books it will be kx, this is ky and it should be kz. But our main motto is it should be looked like an octant. It is looked like an octant. Now the volume of the octant of radius k is, octant is 1 by 8 times 4 by 3 pi r cube. That is 4 by 3 pi r cube is nothing but the volume of a sphere. Okay, here it is looking like an octant, means it is also looking like a sphere, but octant is nothing but 1 by 8 of the sphere. Therefore 1 by 8 into 4 by 3 pi k cube, instead of r cube it is pi k cube. When you are solving this, you will get 1 by 6 pi k cube. Then the volume occupied by each point should be pi by L whole cube. So volume of the octant with radius k is 1 by 6 pi k cube. The volume occupied by each point, octant is nothing but combination of more points, but for each point it should be pi by L whole cube. Then the total number of lattice points in the octant is nu k cube divided by 6 pi cube. Nu k cube divided by 6 pi cube, where L cube is nothing but V. That is that V or nu. You tell me it is V or nu. I think it is V. Okay. V k cube, where V is the volume of the crystal. We already know when there will be this type of vibration taking place, there will be a transverse vibration as well as in the longitudinal vibration in the elastic waves. The longitudinal vibration frequency or velocity of the longitudinal vibration is represented as c suffix L, and for transverse it is represented as c t. Okay, but these are not equal, because CL is vibrating in the longitudinal mode, CT is vibrating in the transverse mode. Therefore the values are not equal. In order to determine the number of possible modes of vibration in the longitudinal mode as well as in the transverse mode, you should find out this Z of V dV in the frequency interval between nu and nu plus d nu. We already know when this type of frequency takes place, two transverse modes will arise and one longitudinal mode will arise. We see in the one-dimensional lattice space also we saw these things. Two transverse modes will appear, one longitudinal mode will be appear. For wave vector, KL represents the longitudinal, KT represents the transverse. Then that formula will becomes, you see, KL is equal to 2 pi nu by CL and KT is equal to 2 pi nu by CT. Okay. Hence the total number of points in the octant with the radii KL and KT respectively are, how it becomes, this is I think V, you change it as V. V divided by 6 pi square, 2 pi nu by CL whole cube, and V divided by 6 pi square, 2 pi nu by CT the whole cube. So Z of V is nothing but 8 pi cube by V, 6 pi cube, 1 by CL cube plus 2 by CT cube into nu cube. This is the main formula. Z of V, that should be is equal to 8 pi cube into V, 6 pi, this is I think pi square, okay, you change it 6 pi square, 6 pi square 1 by CL cube plus 2 by CT cube into nu cube. But the mean velocity is defined by 3 by C cube, that is equal to 1 by CL cube plus 2 by CT cube. You substitute this value here. Therefore, equation 16 becomes Z of V is equal to 8 pi cube V, 6 pi square. Instead of this, you put 3 by C cube. So 3 V cube C cube, that is equal to, solve this, 4 pi V nu cube C cube. So this is Z of V. That is total number of points in the octet. Now you differentiate that equation, you will get Z of V dV is equal to 12 pi V nu cube C cube d nu. Similarly, when you are differentiating the equation 16, you will get Z of V dV or Z of nu d nu, that is equal to 4 pi V 1 by CL cube plus 2 by CT cube nu square dV. This is the very important equation. This gives the number of modes of frequencies which lies between the interval nu and nu plus d nu in the three-dimensional space. In the longitudinal mode, the deflection is along the propagation of direction, but in the transverse mode, the deflection is parallel to the direction of propagation. Here the I think this direction is different. Okay, this direction is different. These two equations are the main equations used in theories of specific heat capacities. In the longitudinal mode, the deflection is here, I think it is not along, this is perpendicular to the propagation of the direction. In the transverse mode, the deflection is parallel. I think it is wrongly written, you just change it. In the longitudinal mode, the deflection is perpendicular to the propagation of the direction. In the transverse mode, the deflection is perpendicular to the direction of the propagation, which leads to two independent components. That's why in transverse mode there are two vibrations. In longitudinal mode there are one vibration. This equation 20 is the main equation which is used in the expressions of theories of specific heat capacity. There are two main theories, Einstein's theory and Debay's theory. So we will see in the next class what will be the specific heat capacity and how the Einstein's theory and Debay's theory works. I think this Einstein's theory and Debay's theory both are studied in SSP in third year BSc physics. I think you may understand the things. We will see on that time. Okay. So this is the modes of vibration in the three-dimensional mode. Okay, so in this class what we saw, mode of vibration in one dimension and mode of vibration in the three dimension. Okay, so we will meet in the next class with these specific heat theories, Einstein's theory and Debay's theory. Hope all are safe. Study well. Meet you in the next class. Okay, thank you. Have a nice day.